we had finished up with the Chapter 11 test. And that's like the last of the purely new content that we're going to see for this course. The remaining things are going to be circling back and resampling some of these ideas from Algebra 2. There'll be little bits of extension here and there, but a lot of it's going to be stuff that hopefully we feel pretty familiar with and pretty comfortable with. So we've made it through like the hardest parts of the course. The last month or two here, we'll just have rehashing some of these ideas that we've seen before. Now these tend to be some of the more difficult ideas from Algebra 2, but you're seeing it for a second time for the most part, which makes life a lot easier. Okay. So we're going to go slightly out of sequence here. We're going to go chapters 14, 15, 11, and 12, or 12 and then 11. Or I'm sorry, 12 and then 13, excuse me. So 14, 15, 12, 13 is going to be the sequence to finish up. And even perhaps if there's time allotted, we have some other stuff that I can do. We'll just see what's left in the school year. Some of these chapters are pretty brief. 14's not too long. 15's the biggest. And then 12 and 13 are both relatively brief. I think 12 is like a 1 day on the calculator kind of lesson. So it's not too much left. All right. So in chapter 14, we're going to be looking at rational functions. So when we talk about a rational function, we talk about something that can be written in the form of a p of x divided by a q of x, where p and q are polynomials. And of course, q of x is non-zero. Now, inside of this definition, we use this term polynomial, which we haven't defined explicitly in this course, but should be familiar from your Algebra 2 course. Remind me again, what's a polynomial? Can you give me an example? That might be a better place to start, of something that's a polynomial. Elena, you're mouthing something. Do you have an example, you think? Okay, like x squared plus a plus b. Sure, that could count as a polynomial, assuming a and b are constants and not variable. But sure. What else? How many terms can it have? Could have more. More than 3 is even okay. Nope, you could have less than 3 too. You could have less than 2. You could have 1, right? So like x is a polynomial. And shoot, even 2 is a polynomial. But you could have like, x to the 75th plus x to the 74th plus x to the 73rd, all the way down to like plus 1. Like that's a polynomial. In general, the way we write a polynomial is it's going to be a coefficient times a power of x. Now the key here is that a polynomial is going to have finitely many terms. You can't have an infinitely long polynomial. That's something else. That's called a power series. It's a calculus topic. But that's kind of what we mean by a polynomial. So the restrictions here for a polynomial, the exponents have to be positive and a whole number, positive whole number, right? So like, you can't have a fraction or decimal in your exponent, right? And your exponent has to be a constant. It can't be a variable. But that's what we mean by a polynomial. Okay? The first thing we want to talk about is domains. So let's say we have the rational function x plus 4 over 2x minus 1. Now remember, a domain is like the set of x values that map to a specific y value, right? So they're like acceptable x's that you could plug in and still get a number back. So when it comes to a rational function, the operations going on here are like addition, subtraction, multiplication, division, right? Of those 4 operations, which is the only one that can give us a problem in terms of a domain situation? Division, great. Why? What kind of division would cause a problem? If we're dividing by 0. So essentially, my domain would be all real numbers except where the denominator is equal to 0. Right? So I can just figure out what that value of x is, right? I can like add 1 to both sides and then divide by 2. So we'd say like all real numbers except for when x is a half. Now, we wouldn't write it this way. We'd use an interval notation to write this. So the intervals that we would write would be negative infinity to a half, union 1/2 to positive infinity. We're going to use parentheses on there. Remember, the parenthesis means that number is not included in the set. Now, the infinities always get a parenthesis because that's not actually a number. It's not a specific value. But the 1/2, the number that's not included, is like the start and end of these 2 separate intervals, right? If I was thinking about this on the number line, so like here's 1/2. The set of x's that I could plug in would be everything below 1/2, and then also everything above 1/2, but not including 1/2. Everybody's okay with that idea? This all sounds familiar, I'm hoping. Now, these places where the denominator equals 0 create a discontinuity in the graph, right? How many of these discontinuities can I have for a rational function? Here we see 1 is possible, right? Can I have less than 1? Yeah. Can I have more than 1? Yeah. How many can I have up to? You can't have up to the degree of the denominator. So finitely many. You can't have infinitely many discontinuities, but you can have as many as you want. Right? If you want 100 of them, you can make a polynomial or a rational function with 100 discontinuities in it. Right? If I asked you for one for 10,000 discontinuities, you could do that. It would take a really long time to write down, but you could do that. Let's do one more example here where we have more than one discontinuity. So let's say this time our polynomial is 3 minus x over x cubed minus 4x. So to find the domain, what do I start by doing? Set the denominator equal to 0, right? So x cubed minus 4x equals to 0. How do I want to solve that? It's a little bit more difficult of a solving problem than the previous one, but still well within your capabilities for everything you've experienced in your mathematics career. This is eminently doable still. How would we want to try to solve this? Any ideas? Hannah. Okay, so the word you're thinking of is factor, but yes, we'll factor out an x. Very good. You're not Nico.
No,
Joey, sorry.
Wouldn't that equal x minus 2 times x plus 2 then?
Great, so we can continue to factor the x squared minus 4. That's a difference of 2 squares. So that would be x minus 2 and x plus 2. And at this point, we factored this thing completely, right? There's no more factoring that can occur. So what's the next step?
Set all three of those equal to 0.
Great, we set each factor equal to 0. This is called the zero product property. You can only do this if the product is equal to 0. Well, there's nothing to do to solve x equals 0. And the other one will add 2, and then we'll subtract 2. So let's write our domain then. So we'll start at negative infinity. And what's the first value we're going to occur? Negative 2. And then negative 2, and the next value should be 0. And then 0, 2, 2. And then 2 to positive infinity. Everybody's okay with that? Again, fairly easy to handle. Okay. So I want to go back here, and we talked about this way back in like the first chapter that we did, so I want to circle back to this now because that was a long time ago. So there's 3 types of discontinuities that can occur. You can have infinite discontinuities. That's the same thing as a vertical asymptote. You can have a removable discontinuity. That's like a hole in your graph. And then you have a jump discontinuity, which is where like the graph is just jumps up a place. It's not connected. Now for rational functions, we can have infinite discontinuities and we can have removables. You won't get jumps. So let's talk about how we can tell where the removable discontinuities and the infinite discontinuities occur. So for both of these are the places where the denominator equals 0. The trick is going to be telling them apart. So let's look at an example, and we'll kind of explain how to do this in a second. Oops. I don't want to write it in factored form. Oops, I should write I'll give that a different name. Okay. So these two problems, one of these has a vertical asymptote and a removal discontinuity. The other has just two vertical asymptotes. But they both have the exact same denominator, which is weird, right? So let's see what's going on here. What you'd want to do to be able to tell which one is going to be which is you'd want to start by factoring both the numerator and denominator. So how do I factor x squared plus 4x plus 4? Excellent. Very good. Just shout them out if you know. And the denominator we already factored above. Joey told us that. Now, once I've written this in factored form, what do you notice we can do? I can reduce, right? What can I reduce? How many? Excellent. One from the numerator, one from the denominator. Okay. Let's do the same thing over here on the other one, and we'll circle back and analyze what's going on. If I look at the next one, how do I factor x squared plus 5x plus 4? X plus 4 and x plus 1. And since the denominator is the same, I already know how to factor that. Can I do any reducing here? No. Okay. So which one do you think is the one with the two vertical asymptotes? The green or the red? The green. Right? And I just find those two vertical asymptotes by setting the denominator equal to 0 and solving. The red then has the one vertical asymptote and one removable discontinuity. Well, the vertical asymptote, I'm going to set the reduced denominator equal to 0 and solve. Well, how am I going to find the location of the removable discontinuity? I'm going to take the piece that I reduced out, that I removed from the problem, and I set that equal to 0. So that's the x-coordinate for that removable discontinuity. But remember, the removable discontinuity is a hole. It's like an open circle on your graph. So that should have a y-coordinate also with it. How do I find the y-coordinate to go along with that? I plug that value for x into the reduced problem. If I do that, I get something that is not undefined because it will not have a denominator of 0. So the location of that hole in my graph is at the point -2, 0. Is everybody okay with that? Let's look at one more quick example here. What if we had taken that red example, but I flipped it? Write this in blue. We already know how to factor these pieces because it's the same problem as before. We just flipped it over. So we can reduce just like we did before. So I get that, right? How many vertical asymptotes is this going to have? One vertical asymptote. And what's the location of that vertical asymptote? -2. Everybody okay with that? How many removable discontinuities is this going to have? Anybody want to venture a guess? It's okay to take a risk, guys. It's okay to be wrong. 1. You say 1. And you said 1 because we have something crossed off here, right?
Yeah.
What would the location of that removable discontinuity be then? Well, -2, right, for the x. But doesn't that conflict with the vertical asymptote's location? Yes, it does. So is there a removable discontinuity? No. And the reason there is not is because the factor x plus 2 doesn't get completely reduced from the denominator. I still have an x plus 2 there. I haven't removed that factor completely because I had an extra one still in the denominator. Is everybody okay with that? So the removable discontinuities are generated when we completely reduce a factor from the denominator, right? If I have an extra copy of it still floating out around down there like we did in this problem, doesn't create a removable discontinuity. Everybody's cool? And this is a piece that, like, I think it's mentioned in Algebra 2, but you don't do a lot with it. But this is hopefully like really kind of solidifying that idea here. Okay. What we're going to talk about next is going to be finding key features for a rational function. So we'll start by vertical asymptotes. How do we find the vertical asymptote? Set the reduced denominator equal to 0 and solve. We wanted to make sure we say reduce there because if we just set the normal denominator equal to 0 and solve, you may catch a removable discontinuity in there also, right? Now, if we're talking about a domain, you don't want to reduce because the removed discontinuities and the vertical asymptotes are both discontinuities. You need to throw those both out when you're doing a domain. But if all you're doing is looking for the vertical asymptote, you need to reduce. Okay. So for removal discontinuity, we're going to set any factors that are completely reduced from the denominator equal to 0 and solve. You'll then plug that x value into the reduced function to get the y. And this is an ordered pair, right? This is an xy, as opposed to a vertical asymptote, which is just an x equals. Maybe I'll write that next to it so we can remember the form of what we're writing these things, right? A vertical asymptote's a line. It's a vertical line, so it starts x equals. A removal discontinuity is a point. It's a hole. It's a coordinate. It has an x and a y. So the zeros, again, that's a point. That's an x comma y, but the y here is always going to be 0. Again, zeros and x-intercepts, same thing, right? So again, we're going to set the reduced numerator equal to 0 and solve. Important that you're using the reduced numerator. As we saw in this previous example, like had you done, well, I guess this one would have been fine. Well, no, it's not. It's, yeah, okay. I guess there's a little bit more to it than that, right? Because if I take this and set this equal to 0, I end up getting the removable discontinuity. So maybe we just say, and also check against So let's add that little context in there, right? So if I looked at this problem here, if I just looked at the reduced, I'd say that 0 would be at -2, but that's the location of my removal discontinuity. So the removal discontinuity supersede that. All right. So the y-intercept is a point, right? That's a 0, comma, y. To get that, we're just going to plug 0 into the reduced function and evaluate, but we also have to check that result against the removal discontinuity. So if you have a removal discontinuity at x equals 0, you can't have a y-intercept, right? Because it'll just be a hole. And then the last key feature we're going to be interested in finding are the end behaviors. These are a little bit trickier because there's actually 3 types. Well, that's not. I'm gonna leave. I might want more space than that. I'm just gonna do them one at a time. So the first situation is where the degree of the denominator is greater than the degree of the numerator. Bless you. When I say degree of a polynomial, what am I talking about? The largest exponent, right? So if it's x squared plus x plus 5, the degree is 2. If I have x squared plus x to the 5th plus 1, the degree is 5. Very easy, right? Everybody's cool? If it's multivariate, it's more complicated, but we're not going to worry about that in this class. So just to put that out there, if I have 2 variables or 3 variables, like x squared y to the 3rd, z to the 5th, plus blah, 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 then the degree is the sum of the exponents in the term. Exponents on the variables, I should say. But we're not worrying about that right now. Okay, in this case, very easy. We have a horizontal asymptote at y equals 0. And I'm going to put an asterisk by the HA, just meaning that if I'm going to call this a horizontal asymptote, but the function might cross it somewhere in the middle. At the ends, it's going to be asymptotic. The function will follow the asymptote at the ends of it. In the middle, it might cross in between. So what I'm saying is that you might have something that does, that, where we cross in the middle, but we follow the asymptote at the ends. We're still going to call that, I'm going to refer to that still as an asymptote. Everybody okay there? The next situation is when the degrees are equal. In that case, again, we get that horizontal asymptote where y equals the leading coefficient from the numerator divided by the leading coefficient from the denominator. And how do we find the leading coefficient for a polynomial? It's the number in front of the biggest variable, or biggest degree variable in the polynomial, right? I'm just double checking. I'm assuming that this is I remember this. Yep, no big deal. I know how to find a leading coefficient, Mr. Cool. I'm just double checking though. I'm just going to say it, make sure. All right. And then the third case is where the degree of the denominator is less than the degree of the numerator. And here we're going to have a call this a slant asymptote, or sometimes it'll call an oblique asymptote. And then the equation for that slant asymptote is going to be the quotient from the polynomial division numerator divided by denominator. That's the worst situation, because you might have to do the polynomial division. And we're going to call these slant asymptotes. But they could have like any polynomial shape. It doesn't necessarily have to be linear. It could be a quadratic asymptote. It could be like a cubic asymptote. I'm just going to call it a slant asymptote because I need to give it a name. But it could just be like a polynomial shape. Okay. So let's do some examples where we're going to find these key features. So we'll just do some examples and run through doing this. Do you guys kind of remember doing this in your Algebra 2 class last year? Yeah. Good. So let's say we have x minus 1 over x squared minus 4. First thing I would do is I'd want to factor this to check to see if there's any reducing that I can do. Probably you'd know right away that there's not. You could look at it and tell without even having to factor it, but that's usually my first step, is I want to do that just to check. So we'll start then by getting the vertical asymptotes. How do I do that? Yeah. So I have x equals 2 and x equals negative 2. How about the removal discontinuities? What are those going to be? Good, yeah, it was a trick question. There are none. If you did no reducing, you can't possibly have a removal discontinuity, right? The act of reducing is what causes those. If you can't reduce anything, there's nothing to do. Okay. How about zeros? How do I find those? Numerator equal to 0. And since there's no removal discontinuities, there's really nothing to check against. I know that whatever I found is my 0. How do I get the y-intercepts? Yeah, plug 0 in. And I'm going to use the non-factored form because, well, it feels just easier. So I get 4 there, so I have the 0.04. And then I'll write OAs just for other asymptotes, whether they're slant or horizontal. We'll make that decision here in a second. Which case have we landed in? Case 1, 2, or 3? The degree of the numerator is 1. Degree of the denominator is 2, so the numerator is less than the denominator. That means that we have horizontal asymptote at y equals 0. Nothing to really compute there. That was pretty easy. Everybody okay with that? Okay. Now, technically, I should be able to take this information and maybe do a little bit more analysis, but should be able to come up with a graph of this pretty reasonably. So let's just kind of, I'll sketch something out here. But I will probably have to do a little bit of end behavior checking. So I'm going to start by drawing in my asymptotes. So there's my 2 verticals. There's my horizontal. There's my 0. There's my y-intercept. Everybody's okay with what I've sketched in here? Notice that I am going to be at least intersecting, if not crossing, the horizontal asymptote in the middle, because I have a 0. That's okay, remember, we said that was okay to happen. It doesn't mean you've done anything wrong. It just needs to be asymptotic at the end. So what I'm going to do now is I need to figure out whether this part of the graph should look like this, or should it look like this? Right, I know I have to be bounded between those 2 asymptotes, but I need to check which one it's going to be going on, right? Everybody's okay with that plan? So to do that, what I'm going to do is I'm going to investigate what's going on the left side of this asymptote. Essentially what I'm going to be looking at is the limit as x approaches -2, and I'll put a negative sign up here to indicate that I'm looking at what's happening at -2 from the left side of f of x. I want to figure out, is that positive infinity or negative infinity, to figure out whether my graph arrow should be pointing down there or pointing up there. Everybody's cool so far? Okay. The way I'm going to do this is I'm going to use my calculator to do this numerically. We haven't talked about in this class, nor would we, how to evaluate a limit without a calculator, or non-numerically. If you take calculus next year, that's where we start, is talking about limits. So I'm just typing in my equation into the y equals. And then what I'm going to do is I'm going to go vars, y vars, function, y1. And I'm going to pick some values that are close to -2, but are still smaller than -2. And I'm going to get progressively closer to -2 as I go. So maybe I'll try -2.1. And then -2.01. And -2.001. And at this point, I'm pretty convinced what part of the graph I have. Should I be drawing the blue part or the green part? The green part, because at -2, the left arrow should be pointing down. So I'm going to do that. Is everybody okay with what I did there? Yeah. Yeah, I'm going to do it like 4 more times, so we'll see it lots of times here. Now I'm going to do the same thing now here on this side. So again, basically what I'm looking for is the limit as x approaches -2, but this time from the right side. So I'm going to be looking at values that are just a little bit bigger than -2, because I want to find out, okay, should I be drawing, something that does like this? Or should I be drawing something that does like this? So I'm going to do the same thing now. So I'm going to do vars and then over to yvars. We're in function mode and we're using y1. That's where we typed everything in at. So I'm going to start at like negative 1.9, something a little bit bigger. And then we'll do like negative 1.99. And then maybe like negative 1.999. And at this point, I have a pretty good notion of what's going on. Should I be doing the red or the green or the blue? The blue again. Or, well, it's not again. So this should be coming down through this. That's pretty ugly looking, but we'll call it good enough. Okay. And then we'll look at what's going on here. What is that limit going to be? So the limit as x approaches 2 from the left of f of x. That's what I'm evaluating here with my calculator. Everybody's okay? And I'm just going to use second and enter here so I can just recall the last thing that I did and just update it. So I'll start with something a little less than 2, like 1.9, and then get progressively closer to 2 without ever passing 2. And what do I notice I'm getting? Is at negative values. So I know that this should kind of just continue heading down rather than like bouncing and heading back up or something. It's going to kind of look like that. And then I have one more piece to evaluate. I need to see what's going on over here. So that would be like the limit as x approaches 2 from the right of f of x. So again, go to my calculator. I'll just press second and enter to retrieve that so I don't have to dance through all those menus again. And just kind of get progressively closer. So 2.1, 2.01, 2.001. But already at this point, I kind of see what's going on. Everything is getting bigger. So my final arrow should be pointing up. So I'm going to do that. So this was positive infinity. This green one was negative infinity. The blue one over here was positive infinity. And the red one was negative infinity. While we're at it, what would this end behavior, how would I write that as a limit? That one I've circled in the light green. The limit as x approaches negative infinity, very good, of f of x equals, what is the y value that that is approaching? 0, right? It's just staying right around the x-axis. It's a y-coordinate of 0. And then over here on the other end, how would I write that limit? The limit as x approaches positive infinity of f of x. And what's that approaching? 0 again. Very good. So again, I'm just trying to connect this limit notation back to the picture. The limit notation isn't difficult, isn't saying anything complicated. The notation is a little bit tricky to get the hang of, but that's why I wanted to like really kind of excruciatingly detailed go through how to use that to get the picture rather than generating points, which you could do, but like, ugh, I'm just going to do these limits and that's going to get me kind of good enough. At least for a sketch. How are we doing time-wise? I still got a bunch of time? Yeah. All right. Let's do another. So again, I think, yeah.
Sorry, so I think it's a good question. But
No,
like,
it's okay.
Y-intercept one, I think it like 4 and that's like 4.
Oh, because I just did it wrong.
Oh.
Where were you? 1/4.
Oh,
No, you should have said something way earlier. We could have fixed this way. That's probably why this thing felt so weird when I drew it. Because that was in the wrong spot. Should be down here. And that feels a lot easier to draw all of a sudden. That's a heck of a lot better. When you see me making mistakes, don't let me keep on making them. Like, if you see it, just holler it out, interrupt. It's okay.
Okay.
Woof. All right, let's do this one. Vertical asymptotes. X equals -3. I'm just going to write down the answers because at some point for something this simple is almost a mental math problem for a lot of these pieces, right? What are the RDs? None. How about the zeros? Good. That's the 0.20. Or y-intercept. Mm-hmm. 0 2/3. And then our other asymptotes. What's the degree for the numerator? And for the denominator? So it's the, nope. Still horizontal. Leading coefficient over leading coefficient. So what's the leading coefficient from the numerator? Oh, okay.
I was wondering if I could go to IT.
Sure, that's okay. No problem. Leading coefficient from the numerator? -1. The leading coefficient from the denominator? +1. So that just becomes -1 over 1, which is -1. Everybody cool? Can I skip drawing the graph? You get the idea, right? It's just kind of a tedious thing, and I'm trying to keep this as peppy as possible. If you guys feel good about drawing the graphs, I'm not going to worry too much about it. The trickiest thing is like being able to write those limits. Getting comfortable with the notation there. That will pop up on the test, so make sure that as you're doing the homework, you're able to do those limit problems. Yeah?
Can we do another limit example?
Yeah, do you want to just write down the limits for this thing? Okay. So from this piece, I can say two things, right? I can say that. Because whatever's happening on my graph that's going to be those ends, right? Is what those limits are representing. And I got my vertical asymptote here. So we're going to have, again, I have to worry about the left side of that asymptote and then the right side of that asymptote. The left side of that asymptote is the limit as x approaches -3 from the left. And then the blue is the limit as x approaches -3 from the right. So the exponent there, the minus and the plus, just is for left is negative, right is positive, because the left on the number line, the smaller things are on the left, the bigger things are on the right. And to evaluate that, then I'm just going to do that numerically. So I'll just go ahead and go in my calculator to the y equals menu, type in my problem into some place. Y1 is where I'm going to type it. Exit back out of there. And I'll go vars, yvars, function, y1. And then I'll start with something a little bit smaller than -3 and just get progressively closer to -3 as I go. And usually after just a couple of inputs, I get the idea of what's happening here. So that's going to -infinity. And if I do the same thing on the right, so I'll start at like -2.9 and just kind of get progressively closer. And I see now what's happening there is things are getting bigger. So that's going to +infinity. So if I were to draw my graph then, would be like down here and then up there. Is that, Elaine, does that feel okay?
Yeah, I calculated it was easy too.
Oh,
Yeah.
okay. Did you get it sorted out?
When y equals like all x's.
Okay. Let's chat for a minute at the end if you don't have it squared away, and I can help you with your calculator. Yeah, no problem. Does the notation feel okay, though, on kind of what we're saying?
How do you get her calculator metric mode?
So you just press the mode button, and then there should be function mode, should be one of the options there. No problem. Okay. So here, this next example, I'm definitely going to start by factoring, right? Just to see. Now, can I factor the numerator? Oh, no, because I wrote down the problem wrong. I meant this to be a minus. Now, can I factor the numerator? Yes. Well, how's it factor? Excellent. X minus 5 and x plus 1. If you're a little shaky on your factoring quadratics, try to get that, review that a little bit, get cleaned up, because we're going to do a lot of it in this chapter, and you want to be fast at it, because it just burns a whole lot of test time if you have to sit there really struggle bussing along doing your factoring. Hopefully they're like 10-second problems. Okay. The point of this, though, is that there's no reducing, which is great for us. So the vertical asymptote is at -2. The removal discontinuities, none. The zeros, okay. Y-intercept, how about -5/2? Right, because everything with the x just drops off. Is how I'm doing that so quickly in my head. Now here comes the bummer, though. If I do this, the degree of the numerator is 2. The degree of the denominator is 1. So what does that mean I'm going to need to do? Polynomial division. Now, remember back to your Algebra 2 class. I know that's asking a lot. There's 2 ways to do polynomial division. Do you remember the names of the 2 methods we used to do it? Synthetic division was one. That's good. Shout them out if you know. Do you remember the other one? We just called it long division, where it looks like the long division algorithm that you learned in elementary school. Now, synthetic division was nice because it was fast and pretty compact, but it doesn't work all the time. Long division stinks because it's slow and takes up a bunch of space, but it works every single time. Do you remember what the criteria is that you need to have to use synthetic division? The denominator or the divisor in your synthetic division problem needs to be leading coefficient 1 with degree 1. What do we have? Leading coefficient 1 with degree 1. So I'm going to use synthetic division here because I am able to. It's okay to do for this problem. If it weren't, you'd have to do the long division. And I think that happens in the homework. Yay! All right. Who remembers how to set up the synthetic division? Right, we set it up. It looks we have this little bar like this, right? Do you remember what number goes on the outside? It's the denominator set equal to 0 and solved. So in this case, that would be -2. Everybody's cool with that? And what goes on the inside? The coefficients from the numerator. So just the coefficients. So 1, -4, -5. When you're writing that, though, what do you have to be careful about? If you skip a term, you need to include a 0. So if this was just x squared minus 5 in the numerator, you have to write 0 x's -5. So if there's a missing term, you need to make sure you write a 0 or it will not work. If you do the same, if you don't put the zeros in for the long division, it'll be messy, but it can still work. It's easier if you do put them in. But here in synthetic division, everything gets mucked up if you forget them. All right, so that's my setup. First step is I bring that first number down, and then I multiply the number on the outside to the number below, and I write it in the next spot, and then add down, and then I just repeat that process until I'm finished. And those numbers at the bottom tell me something. What do those numbers at the bottom tell me? Reading from right to left, which is not the typical way we do things, but reading from right to left, It is the remainder, the constant term, the coefficient on the x, coefficient x squared, et cetera, et cetera, et cetera. So what this tells me then is that x squared minus 4x minus 5 divided by x plus 2 is equal to x minus 6 plus my remainder 7 over my divisor x plus 2. Now, what's the only part we care about? Is the quotient. That's the equation for my asymptote in this problem. I'm pausing here intentionally. Does anybody have a question, a clarification? Need me to repeat something? Okay, very good. Let's draw a picture here. So I'll start with my vertical asymptote. And then I'm going to draw in my slant asymptote next. How do I draw the line y equals x minus 6? How many points do I need to draw that? Just 2, right? It's a line. 2 points is enough. So how do I find points on a line? Pick an x and plug it in to get the y, right? So if I pick x equals 0, I'm choosing that. It doesn't matter what I choose. I'm just going to choose 0. What would the y coordinate be? Negative 6. So let's plot the point 0, negative 6. So 1, 2, 3, 4, 5, 6. And then maybe I pick the x value 6. What's the y going to be there? 0. So I'll plot 1, 2, 3, 4, 5, 6. And I'm going to try to be reasonably accurate here. All right. You OneNote users, who knew you could do this with the ruler thing? That's pretty righteous, isn't it? It's totally righteous, dude. So there's my y-intercept. And then I have 5, 0, and negative 1, 0. Everybody's good here? At this point, I know already how to draw part of my graph, right? I mean, the only way I can connect those 3 points and follow the line or the asymptotes that I have drawn in is to do something like that. Everybody agree? Just for practices, how to write the limit here. This is the limit as x approaches infinity of our f of x equal to, what's that arrow pointing towards? What y value is that arrow pointing towards? Just positive infinity, right? It's pointing up. It's not heading to a specific value. It's just going up forever, right? How would I write this limit? Should probably be a little bit more compact there. Limit as x approaches -2 from the right of f of x is equal to positive infinity because it's pointing up. The last thing I need to do now is figure out whether my graph the other part of my graph should look like this, or if it should be down here looking like that. Everybody agree? Those are the two options. It has to look like one or the other. How am I going to do that? Yeah, I'm going to bust out my calculator and do that limit check thing that I've done before. I'm not actually going to do that because I'm just sick of doing it now. But it's this one down here is what it turns out to be. What I'm more interested in is writing the limits for these two things, because I think that's the place where we're still feeling less confident. Okay? How do I write this one? That's the limit as x approaches -2 from the left of f of x, and it equals -infinity. Great. And then this one over here, that's the limit as x approaches. Nope, it's not -2. -infinity of f of x is equal to -infinity because the arrow's pointing down. Is that feeling any better here, folks? Good. This is one of these that just like practice kind of goes a long way. At this point, you guys should be able to do up through 24. I have one more example that I can do. Well, maybe we'll do that next time. And then start on to the next stuff. But you guys should be able to do up through 24. And I feel like that's a good enough place to stop with just a couple minutes left. I don't think we'll have enough time to do the next one. So